Did you know that many of the stunning and vibrant images of space are not captured in the colors that our eyes perceive? This phenomenon is made possible through a technique known as false color imaging. In this method, colors are assigned to represent specific data values or wavelengths, providing a unique and enhanced perspective that goes beyond the limitations of our natural vision. Let's delve into the world of false color imaging and explore how it transforms our understanding of celestial bodies. Before we begin, if you're new here, don't forget to subscribe and hit the like button to stay updated with our latest content. Now, let's get started. Celestial objects are often observed in wavelengths beyond the visible spectrum to reveal information that may not be apparent in visible light. Different astronomical phenomena emit various types of electromagnetic radiation, and studying these emissions across multiple wavelengths provides a more comprehensive understanding of the universe. In addition to that, false colors are employed for several purposes. They enhance visibility by bringing out details not easily discernible in grayscale or natural color images. They also facilitate the analysis of complex information by assigning colors to different data ranges, aiding scientific interpretation. Additionally, they can be used for artistic or aesthetic reasons, contributing to visually striking representations that capture attention and convey a sense of the intricacies within the data. The human eye is sensitive to a limited range of wavelengths, and false color imaging extends our ability to perceive information beyond this range. Here's how celestial objects are often observed in wavelengths beyond the visible spectrum. Infrared imaging detects heat radiation emitted by celestial objects. This is particularly useful for studying cooler objects like dust clouds, molecular gas, and young stars that emit significant infrared radiation. Infrared observations can also penetrate dust clouds that may obscure visible light. Radio telescopes detect radio waves emitted by celestial objects. This is crucial for studying phenomena such as pulsars, quasars, and cosmic microwave background radiation. Radio waves can pass through cosmic dust and provide insights into processes that may not emit visible light. Ultraviolet imaging observes shorter wavelengths than visible light. Studying celestial objects in the ultraviolet range is essential for understanding the hot outer atmospheres of stars, active galactic nuclei, and the composition of interstellar gas. X-ray imaging detects X-rays emitted by high-energy processes such as supernova explosions, accretion disks around black holes, and hot interstellar gas. These observations provide insights into extremely energetic events that are not visible in the optical range. Gamma-ray imaging observes the highest energy electromagnetic radiation. They are crucial for studying phenomena like gamma-ray bursts, pulsars, and active galactic nuclei. Gamma rays reveal processes associated with extreme astrophysical events. Exploring false color images in astronomy opens up a wide range of fascinating examples that bring the celestial wonders to life. Some notable instances include Curiosity rover Mars. Pictures taken by the Curiosity rover on Mars often showcase the sky in a bluish hue due to image processing and adjustments made for scientific and aesthetic purposes. The Martian sky does have a butterscotch or pale pinkish color, which is a result of the scattering of sunlight by fine particles in the thin atmosphere of Mars. Hubble Space Telescope Eagle Nebula. The Hubble Space Telescope observed the Eagle Nebula, specifically the Pillars of Creation. This iconic image showcases massive columns of gas and dust where new stars are forming. The false color representation highlights different elements and gases, providing a vivid view of the intricate structures within the pillars. The Eagle Nebula has a mixture of reddish hues from ionized hydrogen gas and bluish tones from scattered starlight. Spitzer Space Telescope Orion Nebula. Infrared observations by Spitzer reveal temperature variations within the Orion Nebula, aiding the study of young stars and their surrounding material. False colors help emphasize these temperature differences. The visible light from the Orion Nebula is predominantly pinkish due to the presence of ionized hydrogen. Cassini Mission Titan. Infrared false color images of Titan by Cassini highlight atmospheric and surface features, aiding in the study of the Moon's complex weather patterns and composition. Titan's atmosphere is orange-brown, and its surface, obscured by a thick atmosphere, would appear in subdued colors. New Horizon Pluto. Pictures of Pluto taken by the Ralph instrument on New Horizons are often presented in false color to highlight variations in surface composition and geological features. The Ralph instrument captures data in different wavelengths, and false color is applied to emphasize specific materials or conditions on Pluto. Pluto's surface exhibits reddish-brown and white colors reflecting different types of ices and terrain features. Voyager to Neptune. Voyager 2, a NASA spacecraft, conducted a historic flyby of Neptune in August 1989, providing an iconic false color image of Neptune that highlights the Great Dark Spot, a massive storm in the atmosphere. The image emphasizes bright white clouds, methane absorption bands, and atmospheric features. False color enhances visibility, aiding scientific analysis and providing a visually striking representation of Neptune's dynamic atmosphere. Neptune is not as deep blue as the photo shows. In reality, it bears a subtler, more nuanced hue, resembling a celestial twin to Uranus. The Hubble Palette is a specific set of false colors frequently employed in astrophotography, particularly in the realm of narrowband imaging. Named after the Hubble Space Telescope, this palette assigns specific colors to astronomical features based on the emission lines of ionized gases in the observed regions. The Hubble Palette is often used to enhance the visibility of distinct elements in nebulae, galaxies, and other cosmic structures. The typical color mapping in the Hubble Palette is as follows: Sulfur 2, represented by the color red; Hydrogen alpha, represented by the color green; Oxygen 3, represented by the color blue. This mapping creates a visually stunning and scientifically informative representation of celestial objects. The Hubble Palette is especially effective for capturing the intricate details of nebulae, where these ionized gases are prevalent. By assigning specific colors to different emissions, astronomers can discern and study the varied chemical compositions and temperatures within these cosmic structures. Astrophotographers often use narrowband filters that isolate these specific wavelengths of light, allowing for the creation of images using the Hubble Palette. The resulting false color images not only showcase the beauty of the cosmos, but also offer insights into the physical characteristics and processes occurring within the observed celestial objects. Sometimes, scientists combine observations from different light wavelengths in astronomy to understand celestial objects better. Each wavelength reveals unique details about an object's composition, temperature, and processes. They often overlay these observations using false color images, where specific colors represent different wavelengths. This approach helps highlight various features, like warm dust in infrared or magnetic fields in radio frequencies. By simplifying the data in this way, scientists can interpret it more easily, making it accessible and visually appealing to both researchers and the public. This technique allows scientists to explore the complexities of celestial phenomena and share a more complete understanding of the fascinating cosmic world around us. Interpreting false color astronomical images involves challenges, especially in understanding color mapping choices. Misinterpretation risks arise as these images depart from natural celestial hues. Astronomers assign colors for different wavelengths or features, impacting viewer perceptions. Inconsistency in color mapping can lead to inaccurate conclusions about an object's nature. False color images might prioritize certain features, potentially introducing bias. Scientists must consider scientific goals and the audience in this process. A thoughtful approach ensures the visual representation aligns with scientific understanding, aiding effective communication of complex astronomical data. Creating false color astronomical images involves several steps, from obtaining raw data to generating a visually compelling representation. Here is a step-by-step visual demonstration of this process. Raw data acquisition. Astronomers collect data from a target celestial object using telescopes and instruments sensitive to various wavelengths. This raw data typically comes in the form of numerical values or digital images captured in different wavelength bands. Data processing. The raw data undergoes initial processing to correct for instrumental effects, remove noise, and enhance image quality. This step ensures a clean dataset for subsequent analysis. Assigning colors to wavelengths. Scientists assign specific colors to represent different wavelengths or features within the dataset. This is a critical step that requires careful consideration and knowledge of the physical processes being observed. Color mapping. The chosen color mapping is applied to the data. For example, red might represent longer wavelengths such as infrared, green for mid-range wavelengths, visible light, and blue for shorter wavelengths, ultraviolet or X-rays. This step transforms the numerical data into a visual representation. Combining wavelengths. Multiple datasets, each representing a different wavelength or feature, are combined to create a multi-layered image. This might involve overlaying the datasets or blending them in a way that highlights specific information in each layer. Adjusting contrast and brightness. Fine-tuning is performed to adjust the contrast and brightness, ensuring that important details are visible while maintaining the overall aesthetic quality of the image. This step enhances the clarity of the final representation. Generating false color image. The combined and processed datasets, each assigned a specific color, result in a false color image. This image is a visually appealing and informative representation of the celestial object, showcasing different aspects captured in various wavelengths. Scientific interpretation. Scientists interpret the false color image, extracting valuable information about the object's composition, temperature, and physical processes. The image becomes a tool for scientific analysis and communication. By following these steps, astronomers can transform raw astronomical data into visually stunning false color images that not only showcase the beauty of the cosmos, but also convey complex scientific information in a more accessible and engaging manner. In summary, false color imaging helps us see the universe in ways our eyes cannot naturally perceive. This technique, using assigned colors for different data or wavelengths, reveals hidden details and enhances our understanding of celestial bodies. While it brings beauty and insight, it's crucial to be careful in interpreting these images and understand the choices in color mapping. The step-by-step process of creating these images, from data collection to scientific interpretation, ensures they are not just visually appealing, but also valuable tools for studying and sharing the wonders of the cosmos. Thanks for watching. If you enjoyed the video, please subscribe to stay updated with our latest content. Don't forget to hit the like button as well. Your support means a lot. See you in the next video.